Okay. So far we have been, in the last class we have been considering random vectors. For last few lectures only we have been on this topic. So today we will be, considering characteristic functions for random vectors. See, you remember, earlier we considered only a single random variable, and with respect to a single random variable we consider a characteristic function. So that time it was a function of just one frequency variable omega 1. Then we extended that to the domain of two random variables. So that time also we had a characteristic function. It was a function of two variables, two frequency variables omega 1 and omega 2. So now that whole approach will be generalized to a random vector that has got, say, n number of random variables, right. So we will be considering random x1, x2 dot say xn. Okay, there are n random variables. They are jointly random. They have got a joint density. That is, you can say the joint density, joint probability density. This is for probability. Obviously, you can understand that since there are n random variables, we will have n frequency variables now. Omega 1 associated with x1, omega 2 associated with x2, dot omega n associated with xn. Okay. So the characteristic function, if I define a vector, in my case all vectors are actually column vectors, whereas in the book by Papoulis he normally takes vectors as row vectors. There is a difference you may find. Okay. This is row. If you put a transpose, it becomes a column vector. Okay. So the characteristic function actually becomes a function of n random n variables, n frequency variables, omega 1 to omega n. In fact, it should be this. Take the joint density and multiply it by j omega 1 x1 plus omega 2 x2 plus dot omega n xn, integrate with respect to x1 x2 up to xn. Okay. If I also define a vector x as x1 x2 dot x n transpose column vector, you can also equivalently write this as p of x1 to xn e to the power j. You can see I can always write it as omega transpose x. That is, omega transpose gives you this row vector omega 1 to omega n multiplied by a column vector x1 to xn. If you do this row into column, you will get this term omega 1 x1 plus omega 2 x2 plus dot omega n xn. This is a compact way of writing. Okay. And this is as before. So this is the characteristic function. It's a function of omega 1 to omega n, or since we have put them in a vector form with the name capital omega, you can also call it phi omega. This is equivalent to saying this is phi omega 1 to omega n, in short phi omega, capital omega. Okay. This is a characteristic function. And like before, we had, like earlier we had something called moment generating function, which was phi s. Here also we can have a moment generating function phi s. Okay. Where s is a vector it consists of these elements S1, S2 dot 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 Sn, S1 associated with X1, S2 associated with X2, so on and so forth, and you have got these integrals. Now, it is the power S1 x1 plus dot dot plus Sn xn dx1 dot 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 dxn, which also you can write as p x1 xn e to the power S transpose x dx1 dot 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 dxn. Okay. Obviously, then the characteristic function phi and moment generating function, though I am using the same symbol, I am putting an underscore here. So, that is I say that is phi underscore, meaning it is a defined function, it is a moment generating function whose expression is given by this, and when I just write phi, it is a characteristic function. You can easily see that phi omega is nothing but moment generating function phi bar, where S is replaced by j omega. That is, here if S is replaced by j omega vector, you get back your characteristic function. That is very simple, right? Also, as before, you can get back the joint density from the characteristic function, because after all this is a Fourier transform relationship. Okay. That is, as you have seen, the characteristic function phi omega vector is nothing but, I am rewriting the expression again, joint density multiplied by e to the power j omega 1 x1 plus dot 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 plus omega n xn dx1 dot 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 dxn. You can easily see that this is nothing but Fourier transform of, if this stands for Fourier transform, this function px1 to pxn at these frequencies minus omega 1 dot 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 minus omega n. That is, if you really evaluate the Fourier transform of these, but put a negative sign with the frequencies, then you get this expression. I mean, there is no negative sign that comes in this exponential, okay, because negative and negative cancel, it makes positive. If that be so, then how to get back px1 how to get this back from this? By the inverse Fourier transform relation, 1 by 2 pi integrals minus infinity to infinity dot dot minus infinity to infinity. Okay. This is a Fourier transform at these frequencies, right. So, that means I have to put back phi that is phi minus omega is actually the Fourier transform of this joint density at omega 1 to omega n. Okay. So, joint density is nothing but inverse Fourier transform of phi minus omega. So, phi minus omega, if you put, omega is the vector here, capital omega, that consists of all the elements omega 1 to omega n, small omega 1 to small omega n, and then you have got j minus, this is the inverse relation, right. Omega transpose x, sorry, it will be plus inverse Fourier transform of phi minus omega. So, phi minus omega, you can also write it as phi of minus omega 1, small omega 1 comma small omega 2 minus omega 2 dot 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 minus small omega n. Okay, but I am writing in a compact form using this capital omega notation, and this j capital omega transpose x actually nothing but omega 1 x1 plus omega 2 x2 plus dot 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 this expression omega 1 x1 plus dot 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 omega n xn, nothing else. So, this is the inverse Fourier transform of phi minus omega, right, and you are integrating with respect to these components d omega 1 to d omega n. Now, as before, you can say that if you can make a substitution, say minus capital omega, you can call it omega prime. Okay. So, the integrals limits get interchanged, infinity to minus infinity, infinity to minus infinity, but the differentials d omega 1 now becomes minus of previous d omega 1 and like that. Those minus signs can be absorbed in reversing the limits of the integral again. So, again from plus infinity to minus infinity, you get back minus infinity to plus infinity. So, you get back just, so omega is replaced by minus omega. So, you just get this thing, just a minute. I hope you understand what I said, because I have done this exercise many times in the past. So, I am not doing it again, I am just telling orally. Okay. That is, replace each minus omega 1, replace each omega 1 by say minus omega 1. You can call it a minus omega prime like that. So, this integral limits they get interchanged plus infinity to minus infinity, and all the differentials d omega 1 becomes minus d omega 1 like that. Each minus sign can be absorbed in the integral limits again, so that you get back the original position of the limits from minus infinity to infinity, okay, and no negative sign then. Phi minus 1 minus omega becomes phi plus omega, and in the kernel in this exponential you get a minus sign, which then gives you this thing, that this joint density is nothing but and one thing, this should be 1 by 2 pi to the power n, because there are n variables. I am sorry, I made this mistake. So, 1 by 2 pi to the power n minus infinity to infinity dot 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 minus infinity to infinity, and phi omega e to the power, maybe I erase this here because it is getting bit crowded, congested here. So, it is better I write it somewhere else. So, this becomes nothing but now my minus sign comes omega transpose x d omega 1 dot 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 d omega n. Okay. And as before, you can also say that the characteristic function phi omega is nothing but, after all you are multiplying the function e to the power j omega transpose x by the joint density, that means you are taking expectation of that. So, it is nothing but expected value of j omega transpose x. Okay. Now, a very interesting special case of this, again we have considered that case also in the past in the context of single random variable and two random variables. Here we generalize. Suppose x1 and xn, they are independent. Independent random variables, RV for random variable, and you form a random variable Jade, single random variable, as just their summation. Okay. Each random variable x1, it has its own density, probability density p x1, it has its probability density p xn, but remember I am writing p x1, p xn, they are not the same function. It is not that I have got the same function and x1 is replaced by xn. Actually, I should put p1, pn and like that, but I suppose I can skip this subscript and you can understand that p x1 is just the density function for x1, Pxn is the density function for xn, and they are not the same function. So just loosely I can omit this subscript, because just things become a bit congested if I write equations with so many subscripts and all that, but ideally the subscript should be there. Okay. Or maybe for the timing I can still put it. My question is, given the probability densities of x1 to xn, what is the probability density of Z? First, characteristic function of Z. Okay, what is the characteristic function of Z? Phi Z some omega, sorry. It is not a vector omega, it is a scalar omega now. Phi Z omega, it is nothing but expected value of e to the power j omega Z. Z is actually a function, you can view it like this, a function of x1 to xn. Okay. Now, when you write this expected value of e to the power j omega Z, actually what you do, you multiply this by probability density of Z, again a different function, it is not the same p I wrote, maybe you can put a p z subscript here, into e to the power j omega Z dz, right. But we have also seen earlier that e to the power j omega Z, which is a function of x1 to xn. Okay, there are random variables n and independent random variables given your evaluative function and taking its expectation. That expectation is same as taking the expectation of j omega Z replaced by the function x1 dot dot xn and multiplied by we have done this in the case of single variable and two random variables, that is expected value of a function of some random variable, maybe one or two random variable, is same as replacing in that function those, let me repeat this. That is, suppose you are given a function Z of say two random variables x1 and x2, and then you are evaluating the expected value of e to the power j omega Z. So, multiplying by the probability density and integrating. We have seen, at least in the context of single and two random variables, that is same as evaluating the function first not as Z, but directly as x1 to xn and taking its expectation with respect to x1 to xn. That is multiplying by the joint density and integrating. Both will be same, that we have seen. Okay. If you do that, and that treatment can be extended to the n variable case, that I am not going into, because intuitively that should be clear. So, if you now replace f of x1 to xn by just this summation, because that is how this function is, what you get is e to the power j omega within bracket x1 plus x2 plus dot 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 xn. Okay. And remember, these random variables x1 to xn, they are statistically independent. So, this joint density is nothing but product of px1 into px2 dot 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 into pxn, product of the individual densities, and then multiplied by e to the power j omega, then within bracket this function is nothing but x1 plus x2 plus dot 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 xn, which can be then separated. So, I can have one term p of x1 into e to the power j omega x1 under one integral with respect to x1. Then another term p of x2 into e to the power j omega x2, okay, under another integral, that the integration is with respect to x2, so on and so forth. Okay. That means it is nothing but omega is common, there is only one omega now, that is the difference, because omega came from the characteristic function of Z, Z was a single variable, so it has only one single frequency omega. So, same omega is will continue on all the integrals, multiplied by dot 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 Pxn, I would call it P1, Pn, okay, is the power j omega xn dxn. This is nothing but the characteristic function of x1 with frequency omega dot 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 characteristic function of xn with again same frequency omega. So, that means phi z omega is nothing but phi 1 omega dot 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 multiplied by then phi n omega, right. So, product of several Fourier transforms gives rise to the characteristic function of Z. So, we know the convolution theorem. This means maybe I go into this. So, we got this phi z omega So, from convolution theorem I know if I take the inverse Fourier transform I get here probability density of Z, that will be nothing but convolution of the inverse transforms of these functions. Inverse transform here is P1, okay, but the variable is Z, mind you. The resulting convolution will be convolving, but the independent variable that will come out of this will be Z. So, P1 Z star P2 Z star stands for convolution star PZ PN PN Z. Okay. So, if a random variable Z is formed as a summation of n number of independent random variables, then the resulting probability density for Z is nothing but the convolution of the individual densities of those random variables. Okay. Same result can be extended in the discrete case also. In the discrete case also you can define characteristic functions. Okay. Maybe we can quickly do that. Suppose x is a, we did not do this in the case of single variable or two variables also. So, quickly suppose x is a discrete random variable, it takes values, okay, it takes values from this set, say x1, x2, these are some constant values now, okay, or maybe I replace x because x1, x2 I have already used. It takes values like a1, a2, they are all numbers, maybe 10, maybe 15, maybe 17, maybe minus 10 like that. It can be finite, it can be infinite, okay, dot 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 I am putting a k dot 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 like that. For each value there is a probability, it is not density anymore because it is not a continuous function, it is a discrete function for which. So, p k is the probability of x equal to a k. Then and of course, you can imagine that suppose a1 is 10 and a2 is 15 and there is no number between them, you can assume that there are still numbers 11, 12, 13, 14 like that, but x has probability 0. I mean the probability that x can take the value 11 or 12 or 13 or 14 is 0. So, that way you can say that x is a discrete random variable which takes any value, any integer value from -infinity to infinity, but for certain integers it has got non-zero probability and for certain integers it has got 0 probability. Okay. That way you can define then the characteristic function as a k, if you call this set S, k over S multiplied by p k, sorry, probability multiplied by j. Now, this frequency omega, it is a discrete frequency. it is a digital frequency, its unit is radian. I hope, I mean, you have done little bit of DSP, so you know the difference between discrete time Fourier transform and analog Fourier transform. Here j omega a k, and if I go by the notation of Oppenheim-Schaeffer, then the discrete time, I mean, or the notation used in DSP, this is actually written as a function of not omega, but e to the power j omega, just to emphasize that we get a power series in terms of it is by j omega. So both E and J are constant, omega is the variable, but this is the style of writing, and this omega unit is different from earlier. It is now radian. Earlier it was radian per the unit of the variable. If the x is time, then radian per second. If x is some space, radian per that unit of space, and like that. Okay, but here it is just radian omega. This comes from purely DSP, and then again pk can be found out by the inverse Dtft relation, inverse discrete time Fourier transform relation. Okay, that is pk you can easily see, as you have all studied in DSP, that this function is actually periodic in omega. If you replace omega by omega plus 2 pi, you get the same number because ak's are integers. Okay, and using that you can derive this with the inverse Dtft relation. Only thing is, this exactly not Dtft, because there is a plus sign. So, I will call it Dtft of pk. Dtft is the sequence pk, but at frequency minus omega. Okay. So, inverse Dtft, that means phi e to the power minus j omega is the Dtft of pk. So, pk is nothing but inverse Dtft of phi e to the power minus j omega. So, you can put a minus j omega to start with, and then e to the power j omega n, this is the formula, j omega k d omega. Okay, there is a minus sign to start with, but then you can replace omega by minus omega. Integral limits becomes infinity to minus infinity, d omega becomes minus d omega, that minus sign can be absorbed here. So, you get the same limits again, minus infinity to infinity, phi, I mean you get phi e to the power j omega back, because earlier there was a minus sign, now it has become plus, but in this here it becomes minus. Okay, I do not think I have to repeat this, because similar thing we have done just a while back. Okay. You can generalize this in the two variable case and invariable case. There will be just multidimensional Dtft and multidimensional inverse Dtft. Okay, I am not going into that. Okay. As an example, let us consider Bernoulli trials. Suppose a coin is tossed n times. A coin n times. Okay. Xi is related to ith toss, for I can be I is 1 to up to n. Xi is a random variable. It takes value 1 if head comes, it takes value 0 if tail. So, that means probability of xi equal to 1 is nothing but probability of head, which could be say A. I am not saying that coin is a good coin, it may be biased coin. So, it is not that tail and head they have the same probability half and half, it is more general A, and Pxi is equal to 0, that is xi takes the value 0, is nothing but the probability of tail occurring, which is a B. Of course, A plus B is 1. You can also see that the random variables xi, that is x1, x2 up to xn, they are mutually independent, because one toss has got no influence on the subsequent toss or the toss that was executed before. So, they are independent, right. So, we can use, I mean we know, now suppose Next, we form a random variable Jade as x1 plus x2 plus dot 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 xn. So, out of n trials, we find out Jade. So, Jade can take various values. It may so happen that both x1, x2, I mean up to xn, they all took value 0, that is all were tail. So, Jade minimum value of Jade is 0. Then it can so happen that out of n, 1 is head, rest are tails, then Jade can be 1 and then Jade can be 2 and maximum value of Jade that is permissible is n when all are head. Okay. So, that way one way you can find out what is P probability of Z equal to K. That means K element, K variables take, K of these n variables, they take value 1, that is they correspond to head and rest corresponds to tail. Okay. This we can find out directly by finding out, okay, I mean finding out the probability directly, but we can see, we can show, and we know the expression also, but we can show that by using the characteristic function theory also we get the same probability for P of Z equal to K. Okay. We have already seen, okay, consider the characteristic function of Z. What is the characteristic function of Z? That is e to the power j omega z, and z is from 0 to n. I won't call it Z, it is actually K, sorry. So, Z taking value 1, Z taking value 2, Z taking value 3, each has a probability, and that K comes here, K is from 0 to n. That we have just a while back we have seen the characteristic function for a variable, random variable which takes discrete values, right. So, this is the characteristic function, but we have also seen that if n random variables which are mutually independent are added, then the resulting characteristic function is nothing but product of the individual characteristic functions. Now, what is the characteristic function for, say, the random variable xi? Random variable xi, it can take only two values, 0 and 1, and all others, okay, all others are 0. I mean, for 0 and 1, for 1 it has got a value, I mean the probability of A, for taking value 0 it has a probability B, for taking any other value probability is 0. So, for this, what is, sorry, what is the characteristic function phi I say at omega? Remember, characteristic function of Z at a particular frequency omega is a product of the characteristic functions of x1 to xn, but at the same frequency omega. That omega I choose here. What is phi omega? Phi I omega? Phi I omega means I have to just run this summation, but xi can take only two values for which probability is non-zero. Okay. Xi is equal to, you can say, some integer L, e to the power j omega L. L can be, this is the general formula where L could be from minus infinity to infinity, but we have seen that xi can take only two values, 0 and 1. Okay. For xi equal to 0, I have got a non-zero value of this probability which is B, and for xi equal to 1, we have got a non-zero value of this probability P, that is A. For any other value of L, this probability is 0. That means in this summation I just take, this is a general formula for the characteristic function, okay, but in this case we take only two values, L equal to 0, L equal to 1. For L equal to 0, this is B, and B into to the power 0, that is 1. So, you get term B, and then for xi equal to 1, P of that, probability of that is nothing but probability of head occurring, which is A. So, A into e to the power j omega L equal to 1, so e to the power j omega. So, this gives rise to A e to the power j omega plus B. Okay. And I have to just multiply this probability, this characteristic function. Okay. See, this is the characteristic function for the ith random variable, but it is so general that it is independent of I. That means the characteristic function will be same for all the random variables. So, when I multiply, it is nothing but raising this to the power of n, that is, this is equal to, this is equivalent to now you can use the binomial theorem. You can use the binomial theorem and you will see this is nothing but n c k a to the power k e to the power j omega k b to the power n minus k. So, you can just equate the terms from both sides. This will give rise to probability of z equal to k is nothing but n c k e to the power k b to the power n minus k. This is what is the formula for Bernoulli distribution. We earlier derived it directly, but you see for the characteristic function approach also we get the same result. Okay. We next move to normal vectors, the notion of normality. A set of random variables are given x1 to xn. We will say they are jointly normal and Gaussian they are same, jointly normal or Gaussian equivalently if and only if a1 x1 plus an xn. By the way, I am considering only real valued variables, and therefore, the coefficients that I am bringing a1 to an they are also real valued, but this can be generalized to the complex case, which I am not doing here. Okay. You can also write it equivalently as a vector transpose x vector, where a is nothing but this a1 to an, x nothing but as before. If this is, which is a scalar variable, is a Gaussian RV random variable for any a, that is, you choose any coefficients a1 to an from this summation, you get a random variable, that must be Gaussian. So, if this is true for any choice of a, that you choose any a vector, but the resulting variable is Gaussian, then only it will be called, it will be said that x1 to xn they are jointly Gaussian. Obviously, you can see that if they are jointly Gaussian, any subset also is Gaussian, jointly Gaussian. First, suppose you take a1 to be 1 and a2 0, a3 0, an 0. So, you get back only x1. So, if this is jointly Gaussian, that means x1 is Gaussian. Same for x2, same for xn. Then take a1 equal to 1, a2 equal to 1, rest 0. So, that means, or maybe a1 and a2 non-zero and rest 0. So, that means a1 plus x1 plus a2 x2, that is Gaussian for any choice of a1 a2. That means x1 x2 they are jointly Gaussian, so on and so forth. Okay. All right. Now, we will see. So, this is a general definition. Now, we will see that suppose jointly Gaussian and EXI, they are 0 mean. To make life simple, they are 0 mean for I equal to 1 to n. That is, each has 0 mean, and E of this vector x X transpose, which is in this case covariance matrix, is C, that is covariance matrix. Normally in the case of covariance computation, we first subtract the mean from each random variable, but mean is here is 0, right. So, we simply take X vector in X transpose. You remember we have done this earlier, this is a symmetric matrix, Hermitian matrix. Okay. The structure actually is like this. If we expand it, E of x1 square, E of x1 x2 dot dot dot, E of x1 xn in general, E of xi x1 dot dot dot, general term ith row and jth column xi xj dot dot dot, E of xi xn, so on and so forth. This is called the covariance matrix. Suppose this is given. This is symmetric, obviously. You can take the transpose of this, you get the same thing. E of x1 x2 and E of x2 x1, they are same, and likewise E of xi xj and E of xj xj, they are same, because xi into xj or xj into xi, they amount to the same quantity. Okay, this is, we have dealt with these cases earlier, so I am not getting into the properties of correlation matrix or covariance. In this case, correlation covariance matrix, they are same because mean is 0. Okay. So, I am now we will now show that in this case, that is when they are jointly Gaussian and each has 0 mean and that covariance matrix is C, then the characteristic function, the characteristic function phi omega, capital omega as before is a vector, small omega 1 to small omega n. So, I am not rewriting it anymore. Okay. This is nothing but this exponential minus half omega transpose rho vector, because my omega is capital, my omega is column vector always, unlike Pauli's where the standard definition where he takes the vector to be always in row form, my vectors are in column form. So, I put transpose phi transpose C phi. So, matrix into vector, column vector gets a column vector, row vector into column vector is a scalar number. Okay. So, exponential of a scalar number, but it is a function of all those omega 1 to omega 2, because each omega vector is nothing but, I mean, it consists of all those elements, right. We will show this, and from this also we will show that then the joint density P of x1 to xn, joint density, which will be obtained from the inverse relation actually, will be given by exponential. Always remember this is a general formula for multivariate or multivariable Gaussian distribution. Half x transpose inverse of this matrix C inverse x. Okay. How we do that? We just concentrate on proving this phi omega. Okay. Actually, this part we will not prove, because this is nothing but the inverse transform, Fourier transform of phi omega at minus omega. And if you want to carry out the inverse Fourier transform, then some mathematical exercise will be there. Okay. So, that part if required I will take up later, but that will give you this formula. There is nothing probabilistic or statistical in that, it is just inverse Fourier transform calculation from phi omega at minus omega. Okay. So, we concentrate on proving this fact that characteristic function is of this form. How do you show that? Now, you see, suppose we form a variable z as omega 1 x1 and omega n xn. Since x1 to xn they are jointly normal, z is then a Gaussian variable or normal variable. You can also write it as omega transpose x. Okay. What is Ez? Mean of z will be 0, because mean of z is nothing but mean of omega 1 x1, that is omega 1 into E of x1, which is 0, same here. So, E of z is 0 obviously. And what is E of z square? That is covariance, variance, in this case variance because single variable, or okay, that is nothing but E of omega transpose x, and since it is a scalar number you can take its transpose, because scalar number and its transpose they are same. So, z into z, so this is z, and then I write z transpose, because z and z transpose will be same as long as z is a scalar. But if you take the transpose of z, you get x transpose omega, and you can push this E operation directly on x transpose, because that is the only random part. So, omega transpose C, because E of x transpose is C, there is an input correlation matrix this. Okay. You can see that this you can also write as omega I. So, for particular omega I, Cij omega j. So, forget about omega I, keep it in the outer summation first. This inner summation Cij omega j will give you what? Ith row of C matrix, you are moving over columns, that is you are varying j and multiplying the w's. So, ith row times ith row of C times the column vector omega, you get a scalar number that you get out of this. Okay. That you multiply with the ith element of this omega transpose, which is omega I, and then now do it for all i's. That is how you get this. Okay. Now, you remember one thing, earlier we had considered long back we considered one thing, that suppose there is a Gaussian random variable Z, its characteristic function Gaussian random variable Z, suppose we had shown earlier that if x is single Gaussian variable or normal, Ex is not 0 but some eta, and Ex minus eta square is sigma square, then the corresponding characteristic function for this Gaussian case was shown to be e to the power j eta omega times e to the power minus omega square sigma square by 2. This you have seen earlier. Here also we have got a Gaussian random variable Z, but that has a mean eta equal to 0. So, that we put 0 here. The moment we put 0, you get only this function. Okay, e to the power minus omega square sigma square by 2. Sigma square is nothing but the variance of Z, that is E of Z square, which is this. Okay. That means using this, I erase this part. Using this, we have the characteristic function of Jade, that is E of e to the power j omega z. There is a characteristic function of Z. There is nothing but e to the power minus sigma square. Sigma square is this expression, omega transpose C omega. Okay, you can call it sigma z square. So minus e to the power sigma z square omega square by 2. This is the characteristic function at particular omega. Suppose I took omega equal to 1 now. So this gives rise to e to the power expected value of e to the power jz. What is that? E to the power minus just sigma z square by 2. Okay. But what is e to the power? What is expected value of e to the power jz? That is multiply e to the power jz by probability density of z, integrate. But z is a function of x1 to xn. So expected value of e to the power z can also be written as multiplication of e to the power j, then this quantity omega 1 x1 plus dot 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 plus omega n xn, that is capital omega transpose x, multiplied by the joint density of x1 to xn. Okay, multiplied by the joint density of x1 to xn. Okay, and what is it? There is nothing but the characteristic function of x1 to xn at frequencies omega 1 to omega n. Okay. Let me erase some part and explain this further. But e to the power expected value of e to the power jz is also same as e to the power j, because z is a function of x1 to xn. So, to the power j, you replace z by the function which is nothing but omega transpose x, okay, and multiply by the corresponding densities and integrate, you will get the same expected value. We have, I have just stated a little while back, we have done similar thing for the single variable case, two variable case, and that gets extended to the n variable case. That is, either you take the expected value of e to the power jz by multiplying it by its probability density, that is p of z, integrate, or replace z by its function in terms of x1 to xn, which is this omega transpose x, multiplied by the joint density of x1 to xn and integrate. But omega transpose x, if you put back here, you see that this is nothing but the characteristic function of x1 to xn, that is nothing but phi omega. So phi omega is nothing but e to the power minus, and sigma z square we have already seen, is nothing but this. Omega transpose C omega. Okay. By taking inverse Fourier transform relation at minus omega, you can get the corresponding joint density function. That we have not do exercise. You take that formula for the joint density function. Okay. And finally, that is, you just take the inverse Fourier transform of phi omega. You take the inverse Fourier transform of these at minus omega. That is, you take inverse ft at minus omega, that will give you probability density of this x vector, that is x1, x2 up to xn. So, that inverse Fourier transform integration is just a calculus exercise that I am not doing here, time does not permit, and it is not required. You can just trust me and you can use this expression always, that is I am rewriting only delta is the determinant of the matrix C, I forgot to mention. Where delta is determinant of C. Suppose x1 to xn, they are statistically independent, then obviously C is a diagonal matrix because the correlation terms are 0. Okay. C inverse will give a diagonal, will be a diagonal matrix also. Ith term will be nothing but 1 by sigma I square, 1 by because of inversion, and sigma I square. Sigma I square corresponds to the variance of xi. So, in that case, that is if x1 to xn are uncorrelated, then C diagonal, C is a diagonal matrix, okay. C inverse matrix is ith element, that is the ith diagonal element will be 1 by sigma I square, where sigma I square is the variance of xi, okay, and obviously determinant of C will be, you can see, product of these various terms, sigma 1 square into sigma 2 square into dot 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 sigma n square, because we have got only one diagonal entry. So, in that case, that is under square root, in that case Px becomes just 1 by sigma 1 after square rooting dot 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 sigma n, okay, 2 pi to the power n square root into exponential minus 1 by 2 sigma 1 square minus 1 by 2 sigma 2 square dot 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 minus 1 by 2 sigma n square. It amounts to just multiplying n individual Gaussian density functions for n random Gaussian random variables that have 0 mean and variances sigma 1 square, sigma 2 square dot 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 sigma n square. So, we stop here today. In the next class, we talk about stochastic convergence and we go towards central limit theorem. Okay. Thank you very much.